Hi, thank you all for joining us today at Vamos. Before I introduce our speaker, I just wanted to let everyone know that we'll continue with our practice of a post-seminar discussion. So a Zoom invitation to a separate room will be issued at the end of the talk, and we encourage everyone to join who is interested in speaking with James today. To promote student and postdoc participation, we kindly ask faculty to leave this discussion after 10 minutes, which will be hosted by a student as well as two faculty moderators from among the panelists. Okay, so it's a pleasure to introduce James Thompson of JILA in Boulder, Colorado. James is a scientific leader in the creation and application of quantum entanglement to metrology, contributing to many key milestones in this now really broadly engaged endeavor. He's also quite active in the field of laser science, in which during his time at JILA, he implemented a fundamentally new and intrinsically robust kind of laser. So please join me in welcoming James today to Vamos.
Great. Thank you so much to the organizers for inviting me to talk today. This is going to be a fun experience. I'm going to tell you a little bit about how we create twists, gaps, dynamical phases, and superradiant emission on very ultra narrow transitions, in particular in 87 strontium. So this work is being done, as Adam said, here at JILA in the Department of Physics at the University of Colorado. So here's the basic idea of what we're going to do. We're going to put a lot of atoms, which are these little orange dots here, inside of a cavity. And it turns out in atomic physics, we know really well how to actually manipulate and control those atoms, those single atoms. But what we're interested in is going beyond just sort of single atom control and moving into a regime where we can create correlations and entanglement between the atoms. This is kind of sort of represented by these kind of links between these atoms. They're not independent atoms doing their own thing in parallel. And the way we're going to generate those links and correlations is going to be by using a photon bus. We're going to use an optical cavity to help create those correlations. And so in doing this, today I'm going to tell you about how we're trying to use all the aspects of quantum mechanics. To do this, we're going to look at generating unitary dynamics, using the quantum measurement process, dissipation, and the full range of tools that are available for creating this kind of correlation and entanglement. So I'm not going to show very much of experiments at all. So if you're looking forward to seeing experimental apparatus, this is it. And so what you see here is an optical table, and there's another optical table you can't see back here, devoted to a strontium cavity QED experiment. There's a table over here, which is a rubidium cavity QED experiment, and another table associated with it. And in fact, there's another table. This is a little bit old, sort of sitting right here in the middle now, which has a third strontium experiment. They're all involving putting atoms inside of optical cavities. So for instance, here's the rubidium experiment. These are big macroscopic cavities. The mirror separation here is about 2 centimeters. And here's a magneto-optical trap of rubidium atoms fluorescing inside that cavity. In all of these experiments, we're going to take atoms that are trapped between these cavities, and we're going to load them into 1D optical lattices so they're well aligned and registered with respect to the optical cavity modes. And with respect to the axial dimension, they'll be in the lambda-Q regime. So essentially, we eliminate Doppler broadening in these systems. Here are the two cavities associated with strontium. So what you see here is a cavity spacer, and there's a mirror here and a mirror here. And that little blob right there is our mod of strontium atoms. This is the latest system, and it's kind of our stealth cavity. It's been painted black to avoid stray light reflections, but it's actually a ring cavity. And so there's actually a triangle that's formed here with 3 mirrors. We're going to try and load strontium atoms into an arm here to try and create a continuous superradiant laser. So what we're doing is trying to exploit not just single atoms, but many atoms. And I'm going to talk about 4 main topics today. How we are trying to generate ultra-stable, what we call superradiant lasers, which are kind of an optical equivalent of a microwave maser. I'm going to tell you about how we can use the cavity to generate cavity-mediated interactions. We can observe them on an ultra-weak transition, a transition that's only 1 millihertz wide. How we can go to a slightly broader but still narrow transition, a 7.5 kilohertz transition, and observe a dynamical phase transition. And lastly, I'm going to talk about how we can use in a rubidium system what are called quantum non-demolition probes to entangle the atoms with each other via measurement. I didn't put it on here, but if I had right here in the middle, if I have time, I'm going to talk about how we've made measurements of actually this natural line width of the strontium atom, which is used for instance, some of the most advanced optical last clocks in the world, as well as an emerging technology for matter wave interferometry. So let's talk about the first topic. The first topic is going to be trying to break through thermal limits and technical limits on laser frequency noise. And the idea here is we're going to hide the laser's phase information in a collective state of the atoms rather than in the photon field. And the goal ultimately is to see if we can generate ultra stable and robust lasers for many different applications. So before going into sort of what we're doing new here compared to other approaches, let me remind you of the other approaches. If I want to make a really, really stable laser in the lab, and that's a really great thing because you need stable lasers to, for instance, coherently manipulate atoms. Or if you want to establish, for instance, very long baseline interferometry, you need these very stable lasers. Let's say just arbitrarily that I want a fractional frequency stability of 10 to the minus 17. So sort of the line width of my laser divided by the center frequency is 10 to the minus 17. Well, the way that it's done now is you take a mirror here and a mirror here and you put them on a spacer and you just try and hold that separation very, very fixed to define a resonance condition. And then you compare the frequency of your laser to the frequency defined by the spacing of these mirrors, and you steer the laser to match the resonance frequency of this reference cavity, okay? Which is essentially an arbitrary length reference that you're trying to establish. So let's come back to this 10 to the minus 17 number. If you want to do that, if we say that the mirror spacing here is 1 meter, that means you need to control the average separation between these mirrors to 10 to the minus 17 meters. Now, let me remind you, the size of a single nucleus is 10 to the minus 14 meters. This is really, really hard and challenging to do, but it's amazing progress has been made in actually building ultra stable systems where you can kind of get into these, you're approaching these kinds of frequency stabilities. What ultimately limits this is not only the fact that, for instance, someone could be walking around the lab and causing things to vibrate, but also the fact that this is a macroscopic material that's sitting at room temperature, or maybe in a slightly cryogenic environment, let's say, around 4 Kelvin, 17 Kelvin. But there's actual thermal Brownian motion that actually causes the atoms in this object to wiggle and jiggle. And that changes the separation between the mirrors and causes the resonance frequency to change. And so this actually is a hard and challenging problem. It's been very, very difficult to get around. And so there was another approach that was proposed, which said, look, rather than building some kind of like artifact length reference here, let's actually try and build a laser that extracts light directly from high Q optical transitions. Transitions that might have natural radiative lifetimes or line widths of a millihertz to a hertz. And so these exist in things that are used commonly for clocks, such as strontium, ytterbium, calcium, or magnesium. And this idea was put forward here at JILA and as well in a group in China. So what we're really going to do is try and build a kind of laser here where we're going to use these very narrow transitions as the gain medium for the laser. But now let me sort of point out the difference between what you might think of as a standard optical laser here versus what we're going to build in this case, okay? In a standard optical laser, the cavity line width, which in this talk will be referred to as kappa, is actually very, very narrow. Whereas the line width of the gain medium, in this case, the atoms here, is actually very broad. It has a line width gamma perp. So the gain medium is very broad, the cavity is very narrow. In this case, if you think about which is more coherent, the atoms here or the cavity, it's actually the cavity that's more coherent. And so here the photons inside the cavity are the flywheel or the phase memory for this laser. As a result, if I move the mirrors, I'm going to change the resonance frequency, and it turns out the lasing frequency or the oscillation frequency is going to follow the cavity resonance frequency 1-to-1. If we go to a different regime, which is the regime of this talk, we're going to have the roles reversed. The cavity line width, gold here, kappa, is actually very broad, whereas the gain medium is going to be super narrow. And now, in some sense, we're flipping the roles that the atoms are going to be the more coherent thing and are going to act as the flywheel or phase memory for this laser. Should the laser be putting out a cosine right now or a sine wave? And it's going to be the atoms that are going to keep track of that. As a result of that, it turns out that if I wiggle or jiggle these mirrors and I put some phase shift on the light that happens to be inside the cavity at that moment that I move the mirrors, that light escapes quickly from the cavity and new light with the correct phase is put into the cavity immediately that doesn't see the defect in phase caused by the motion of the mirrors. All this is to say that the oscillation frequency or phase is really going to follow the atomic frequency or phase now. So when these proposals were put out, we did a proof of principle experiment using Raman transitions to mimic ultra-narrow transitions in our rubidium cavity QED system. And in fact, we were able to show that we could really get into this limit where on average, we could get lasing with as few as 0.2 photons inside the cavity. And it really said at that point, just because of number phase uncertainty relationships, really, this just was a proof of principle to say, look, you really can store the phase information inside the atoms. So that led us to building a new experiment that I'm going to tell you about, where we tried to generate lasing on an ultra-narrow atomic transition. It's the a transition that has a natural line width of 1.35 millihertz or a lifetime of about 118 seconds. I will remind you that that's crazy long. You can absorb of order an EV photon, and this atom can just hold on to it for longer than I'm going to spin on the slide. It's really nuts. Okay, so now we're going to do something even nuttier, which is we're going to turn something that doesn't like to emit light, and we're going to use it as the gain medium for our lasers. We're going to pack about of order 100,000 to 1 million of these atoms in between two mirrors. We're going to try and get them to laze for us. By doing this, we actually get a collective enhancement in the output that essentially the radiated fields from each of these little dipoles coherently add. So the power goes like, the electric field goes like N, but the power goes like N squared. So this is going to be work. So there had better be a win associated with it. So how much might we win? Well, there's been a lot of theory related to these types of lasers operating this domain. So I'll point you to the theory down here. But some of the wins that we could hope is that by hiding the phase information primarily in the atoms, we could be more than 10,000 times less sensitive to cavity frequency noise. That would be a huge win for a problem that's been ongoing for decades now. And so to have such a sort of a big win in terms of like thousands and thousands of times less sensitive, that would be worth doing. But there are also fundamental quantum noise processes, and it turns out that you can predict that the equivalent of a shallow town's line width for this laser, essentially a phase diffusion line width, ends up going like the single particle cooperativity parameter of cavity QED times the excited state natural decay line width, which is this line width up here. And so if you put that in, it turns out that you can predict that the quantum mechanics would limit the line width on this transition for our system to be of order of millihertz or less. So this seems really, really encouraging. So we tried to build this system, but I'd like to sort of talk about stimulated emission for just a minute and give you a picture of it. So let's start with something that a lot of us are very, very comfortable with, and that's stimulated emission in the terms of Rabi flopping. Okay, so I apply a laser to an ensemble of atoms in here. Here's my laser, and it's got this field, and I apply that laser, and if I put the atoms all in the excited state here, here's my ground state, then I describe that as a collective block vector pointing towards the North Pole. And if I turn on this laser, what's going to happen? Well, I'm going to create a drive which couples E and G, and it's going to cause atoms to go from E to G and back. Okay, and so this is called Rabi flopping. We can describe this on this block sphere as this laser light creates a fictitious magnetic field that torques the spin. Okay, and so the fictitious magnetic field is here. You get a cross term right-hand rule, and you get a rotation. Okay. So that's something we're all familiar with. So now I want to tell you that after the initial dynamics, we can actually think of what we'll call superradiants in the regime we operate as essentially a kind of self-driven pi pulse. Okay. So the idea here is that the atoms start in the North Pole, and then a little bit of spontaneous emission from those atoms leaks a little bit of light into the cavity. And essentially that leaking of light is generated by the dipole moment, which is a quantum fluctuation of sort of the orientation of this block vector at the North Pole that radiates a little bit of light and creates a little bit of a torque axis, creates a little bit of a fictitious magnetic field. And then it becomes a runaway process because having actually created a little bit of fictitious magnetic field, it actually causes the dipole moment to grow, which causes the fictitious magnetic field to grow. and it becomes a runaway process. And actually what you see, if you look at the output from this object, if we let light leak out through one of the mirrors, we see the output power starts low, 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 builds up to a maximum, and then goes back low. And in that process, all the atoms will be transferred collectively from the E state to the G state. So we expect to see this kind of buildup of light and going away. It's not single particle physics. It's really that collectively atoms are emitting light into this cavity and stimulating each other to go to the ground state. So in 2016, we were able to pack a lot of atoms inside of our cavity. We put them all in the excited state and we wait. And what we see is, as a function of time, this is in milliseconds. After about, here about 75 milliseconds, using 200,000 atoms, nothing, 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 and then the output power from the laser goes up and comes back down. And this is this kind of superradiant pulse of light in our system. So this is exactly what we wanted. We're above threshold. Is essentially single particle decoherence isn't keeping this from happening. And so this is the regime we need to be in. We can also look at the scaling with atom number, because we said that the output power should scale like the number of atoms squared. And so we can look at the peak output power for various atom numbers here, and we can plot that over here. And sure enough, we see an n squared scaling, except there's a threshold atom number. That threshold atom number is set by essentially how big is the single particle decoherence in the system. So we saw this in 2016. Earlier that same year, before this work, we had actually seen this kind of physics. And even in a crossover regime between sort of a standard laser and a superradiant laser on the 7.5 kilohertz transition in strontium, as well as more recently, the same transition, this kind of physics has been seen in Jan Thompson's group. Also, in about the past year and a half, Hamiltonian's group has seen this in calcium on a narrow transition as well. So not only can we detect light coming out of the cavity, but we can also take its spectrum. And the way we do that is we take advantage of the fact that June Yee's lab is just down the hall, and they're wonderful to collaborate with. And so what they do is they take some of their light that's been stabilized to this very, very stable optical reference cavity. This is a real Ferrari of reference cavities. It's really, really fantastic. And we build a fiber phase noise cancel link down to our lab, and it allows us to essentially take the pulse of light that comes out of our cavity and do a heterodyne spectrum of that pulse of light. And so here's the heterodyne power spectrum of a single pulse of light coming out of the cavity. So this is in frequency space, not time domain. Okay. And you can see that it's very narrow and that it's essentially Fourier transform limited. It's just the fact that the pulse lasts a very small amount of time. So far I've been talking about the excited state as a single excited state, sort of a triplet P0 and a singlet S0 ground state, but in fact, there's nuclear spin in this atom. And so in fact, there are multiple ground and excited states. And we can actually do experiments now where we actually optically pump half of the atoms into the -9 halves nuclear spin state, and the other half of the atoms into the +9 halves state. And we can actually have them emit light simultaneously. So if we take a spectrum of that light when it comes out, what we see is a peak corresponding to light being emitted on the -9 halves transition, and a peak corresponding to light being emitted on the +9 halves transition. One thing that's really great about that is that these have opposite magnetic field sensitivity. So for instance, what we can do is we can vary a magnetic field applied to the system in the lab, and we can look at how the two individual peaks shift and plot them versus each other. And you see that they're correlated. So in fact, if we just look at their sum or average frequency of the peaks, we see that that's magnetic field insensitive. So this actually gives us a built-in single shot rejection of magnetic field noise in the system. Also, you might, if you were really paying attention, you might notice there's a little peak here and a little peak here, and the same over here. And what that's corresponding to is, well, we didn't do a perfect job of optical pumping. Okay, so we have some atoms in these other states, and we're seeing light from these other transitions. So rather than having a little bit of light in those states as a mistake, we can actually just equally populate all of these states. And here's the output power as a function of time. Now I have all these transitions emitting light, and the frequency difference is integer steps in the differential Zeeman shift between neighboring states. And so what you actually see is that you go from constructive interference, and at a later time you get destructive interference among all those radiating dipoles, and then it goes back to constructive interference. So you go between sort of bright phases to a dark phase to a bright phase. And so this really allows for the idea of, for instance, a hybrid active passive oscillator where essentially you could measure the phase of the total dipole moment of all of these summed. And then we've shown that we can actually adjust the magnetic field in real time to freeze them in this dark state. And then break that dark state at a later time by changing the magnetic field again, and then measuring the phase of the light that comes out. So there's a lot of fun games that could be played there. So when we operate this system, we are essentially operating it almost always in this regime where we're optically pumping half the atoms into -9 halves and half into +9 halves. So we're magnetic field insensitive. And then we can construct that average frequency and we can look at a fractional Allen deviation, which if you want to think of it as kind of like a delta F over F. It's the fractional frequency uncertainty as a function of how long you measure for. And so when we do that, that's described in the paper up here in a collaboration with June Yee's group down the hall. We see that the fractional frequency instability at 1 second is about 7 to 10 times 10 to the -16 at 1 second. Depends on how we tune it up. You can ask what limits that. Well, it turns out that about half of that short-term instability is coming from photon shot noise. What's going on here is that we have a pulse of light that's Fourier transform limited, and we're collecting of order 0.05 photons per atom. And that's limited by quantum efficiency. So if our quantum efficiency were 1 in our detection process, that would be 1 photon per atom is about what we think. Okay? And then it's a question of how many photons do you have to split that line by? And so if you had more photons, you could split the line by more. So that's about half of the limitation here. The other half is actually coming from the noise associated with this optical reference cavity. And again, we're very happy about that because this is a really, really good optical reference cavity. And to even be in the same ballpark for one of the first experiments to ever do this, we're happy about that. It seems promising. So that's about precision. I'll also comment that we've done an evaluation of the absolute frequency accuracy. I won't go into too much detail here, but essentially what we did is we compared the light from our superradiant laser to light from the reference cavity, while the same light from the reference cavity was also being used to probe an optical last clock in June Yee's lab. And we could constrain that the difference frequency was 2 ± 4 times 10 to the -15. So it also has a high degree of accuracy, not competitive with the best optical last clocks, but again, we weren't necessarily pushing this number. We were more interested in the precision side of things. So at the beginning, I said that one of the promises was that we could be much less sensitive to cavity frequency noise. And so we can go in and actually ask, what's that insensitivity factor? And the way we can do that is if we have a cavity resonance frequency in blue here, we can actually use piezo's to shift that cavity resonance frequency to a new frequency, okay, by changing the length of this cavity. And then we can look at the frequency of the light coming out in the first configuration and then in the second configuration. We can ask how much does the laser frequency change by? Now, if this were a standard laser, that ratio of the change in laser frequency to the change in the cavity resonance frequency would be 1 to 1. Okay. What we do when we see this is we see that the change in the laser frequency is on the vertical here. Here's the change in the cavity resonance frequency. And for scale, this is kilohertz, whereas the scale here is hertz. And it's even relatively flat on this scale. Okay. So in fact, we're very, very insensitive to cavity resonance frequency. If we compute this, that ratio is about 2 times 10 to the -6. And so this is really encouraging. This is one of the big wins we wanted. It says we're immune to thermal and technical vibrations. And so beyond just sort of giving a very stable reference, say in a science laboratory, maybe it will even be deployable one day outside the science lab, well beyond what I can do in terms of engineering, but it gives you a very, very strong lever arm for thinking that way. So having established pulse superradiance, I'll just tell you that we're actually building a third experiment, which is this ring cavity that I was talking about, where we're going to try and go from pulse lasing to continuous lasing, CW lasing. So this is being led by Julia Klein with work input at the beginning stages from Juan and Dylan in the lab. The cavity mode here is a ring cavity, and the idea is that we're going to have a 2D MOT, which is all this blue glow up here. It's going to come through some baffle, and we're going to load atoms into this lattice, and essentially they're going to be transported inside this cavity and sort of lays in this region down here. This is a hard and challenging problem, but the reason we're trying to tackle it is if we look at our previous Allen deviation, it turns out that with simple scaling arguments, And there may be other problems along the way, but with the simplest scaling arguments, the potential frequency stability of the CW source could reach better than 5 times 10 to the minus 18 at 1 second. And that would be a really phenomenal short-term stability. So I think I'm actually going to pause there and see if there are any questions.
Perfect. So we've gathered a couple questions, but before I pass them along, I wanted to remind everyone that they should feel free to put questions either in the Zoom Q&A or in the chat with the YouTube feed. And we always encourage questions from students and postdocs. So really feel free to post stuff. So we have a few questions. So we have a cluster of questions where basically people are trying to understand what's really the role of the cavity in the superradiant laser. Like how is it different from locking a regular laser to a good cavity? And if all the coherence is in the atoms, then what's the cavity actually doing?
Okay, so let me answer both of those separately. So what's different from locking to a standard cavity is this. If I change my normal length of my reference cavity, the laser that I'm locking to would change by the same amount. And it's this fact that actually now, even if the cavity wiggles and jiggles around the atoms, it doesn't matter. We're about we can be as much as 500,000 times less sensitive. Okay. And so that would be my answer to the first question. But then the other question is, well, if it's all in the atoms, what's the cavity have to do with it? And I think one way to think about it, at least one possible answer is, it turns out that you really need high optical depth to get above the threshold for seeing the superradiance, okay? And so what you're really doing is you're essentially using the cavity to multi-pass field through the atomic ensemble as a way of effectively increasing the optical depth so that at a given amount of single particle decoherence, you can still be above threshold for lasing. What does it mean to be above threshold for lasing? In this case, what that means is that actually this buildup time to actually seeing a pulse of light, if it turns out as you're building up this sort of pulse, if it turns out that single particle decoherence is destroying it as fast as it's trying to build up, then it never gets above threshold and you never see a pulse of light. So the role of the cavity is essentially there to help push us above the threshold for actually getting lasing. There are other reasons, but let me stick with that.
Okay, great. Thank you. That's very helpful. We also had a couple of more atomic physics questions. So basically, one from Dima Budker is, how do you actually get this optical pumping exactly or almost exactly into the two stretch states? And then Shimon was wondering if this 1 millihertz transition is somehow ideal, or would you eventually want to go to something even narrower, or which there are options for?
Okay, so let me handle both of those somewhat separately. So for the into the minus 9 halves and plus 9 halves, it turns out that we optically pump on a singlet S0 to triplet P1 state. And there's an F equals 7 halves version. So if you replace that with 1 and 7 halves here, then it turns out if you apply pi polarized light, the two dark states in that stage are the plus and minus 9 halves states. So it's the typical type of game you might play. For instance, if you were doing rubidium, you might be familiar with, if you had F equals 1 ground state, you could optically pump with pi polarized light on the F prime equals 0 excited state. That'd be an example. Okay. The other question was from Shimon, and that was, is another line width better? Let me just walk back to this one. So it turns out that actually what sets the quantum limited line width here is going to be the single particle cooperativity times gamma, okay? And so in some sense, actually we could work with a lower finesse cavity or a cavity with a higher modeway size to work at lower C. And if we did that, then we could work with a with a transition that actually has larger gamma. And so for instance, actually, maybe there would be some benefit for not working directly with the millihertz transition, but if you had something that was like 10 millihertz or 50 millihertz. But there will be various trade-offs in terms of total output power. So there's always a game you're playing here between output power, cavity frequency pulling coefficient, and quantum limited line width. But there's actually degrees of freedom. So it's not clear that going to gamma smaller is actually better. There are probably better ways to access the interesting physics other than turning down gamma.
Okay, so then maybe we'll ask you one more before letting you move on. And so this
Sure.
is a question from Aruku Senu, and he's basically he's noticed that you get this sort of pulse of superradiant emission, and how do you make a CW laser from that, or does it actually not matter that it's pulsed?
Yeah, so it definitely matters in the sense that if we're only getting information for about 50 milliseconds once a second. We could improve that and stay in pulse mode, but that's what we're doing now. You'd really like to have a continuous phase record. In fact, I think one of the things about going to CW that will be really exciting is that you're really going into a regime where you're talking about phase locking compared to frequency steering. And we can start thinking about phase locking in a change in language there. So essentially the way you would like to go to continuous is if you had a cold atomic ensemble, once an atom is decayed to the ground state, you'd like to actually use some other state I haven't drawn to optically pump the atom back to this state and do single particle repumping. In our system, we have that capability that we're building up, but actually we realize these are cold atoms. And so our plan is to initially try and just actually deliver a large flux of atoms into this lattice so that they give up their stored excitation from the excited state, and then we actually kick them out as a function of time. So we're just going to feed more atoms into the system.
Okay, great. Thank you very much. I think we'll let you continue then.
Sure. Great questions. Thank you, everyone. So I'm going to tell you about how, up to this point, I've been thinking about this more from a precision measurement perspective, right? Thinking about metrology or ability to measure things. And now I'm going to talk about how we can view the system of atoms interacting with the cavity as more of a kind of a many body system, okay? And I'm going to talk about how we can see that the cavity can mediate spin exchange interactions between the atoms, okay? And so this is actually a collaboration between our group and Anna Maria Ray's group here at JILA, and most of the work I'm talking about can be found in this reference. So I started with this very simple picture of Robbie flopping. And I said that, look, this kind of when you're on resonance with the cavity mode, so I've tuned my cavity resonance frequency to be on resonance with the atomic transition frequency, FA. And in this regime is where we see superradiance. We described it as, well, the atoms, this block vector actually, it begins to have a dipole moment which radiates some field into the cavity that I described as a fictitious magnetic field, which causes it to rotate faster down, which causes it to radiate more field. Okay. What's important about this is if I take the projection of that block vector onto this plane, the radiated field by the dipole moment actually causes a response that creates a fictitious magnetic field that's 90 degrees to it. So now let's take another limit. Let's imagine that we take that optical cavity, we tune a voltage on a piezo to change the length of the cavity and shift the cavity resonance frequency off of resonance now from the atomic transition. Well, that cavity is basically a harmonic oscillator. And what do we know about harmonic oscillators? Well, compared to when you're driving a harmonic oscillator on resonance, when you drive it off resonance, in fact far away, you get a pi/2 phase shift in the response of the harmonic oscillator to the drive. And that pi/2 phase shift, that 90-degree phase shift, corresponds to now the fictitious magnetic field gets a phase shift on it and is actually going to be oriented here. It's actually underneath the block vector. And now you see that this is not going to drive decay of the atoms. It's actually going to try and deflect the block vector. In fact, if I just thought of this as an applied external field, it would just cause the block vector to want to precess around this fictitious magnetic field. So all of this was caused simply by tuning the cavity off of resonance with the atomic transition frequency. So now I'm going to claim that this actually leads to the emergence of what looks like a spin exchange interaction. So let me give you an argument for why we can describe it that way. Well, if I have a classical, dipole interacting with this fictitious magnetic field, the Hamiltonian looks like J dot B. But now what we've just said is that this fictitious magnetic field actually, lies directly underneath the block vector J. It lies in this plane. It's Jx hat plus Jy hat. So now let's actually just plug that in for this magnetic field. And we'll see our Hamiltonian looks like Jx squared plus Jy squared. So let's define a funny symbol here. We'll call it J plus minus, and that's equal to Jx plus or minus Ijy. And now we can rewrite this term as J plus times J minus. And now we're going to add hats on top of these J's, and voila, we're doing quantum mechanics. And we call this a spin exchange interaction, okay? But every argument I've made to this point is completely classical, okay? But this is how you can get to see where the spin exchange interaction emerges from. You have to put some coefficient in here, which has to do with sort of what's the size of the field that's actually inside the cavity and sort of sets the strength of this interaction. You can think of this J plus J minus, these collective raising and lowering operators acting on the block vector J, as essentially single particle terms that correspond to flip-flop interactions. In other words, an atom in the ground state and an atom in the excited state, they exchange a photon via the cavity, and now that this atom is in the excited state and this atom is in the ground state. And so sometimes these are called flip-flop interactions. So we'd like to get into a regime ultimately where we can have these flip-flop interactions described as some strength chi, but not actually have a lot of dissipation from the system. We'd like to have a closed quantum system. And you can ask, what's the characteristic rate at which light comes out of the system due to superradiance, which is a collective effect. And it turns out you can see that there's a 1 over detuning squared scaling in a large detuning limit. Another way to say this is, well, there's field inside the cavity and that leaks out. And the rate at which atoms decay from the excited state to the ground state due to this leakage goes like field squared, okay? In contrast, let's think about this coherent interaction over here. Well, this is actually just essentially a field, this fictitious magnetic field, torquing another atom. So you've got some field inside the cavity, and it torques another atom. And so this chi then actually just goes like 1 over detuning in the large detuning limit. And that's because it goes like the intercavity field, not the intercavity field squared. So by going to very, very large detuning over here, we can actually, both of them get smaller, but this term gets smaller more slowly compared to this term. Okay. And so that means that we can actually detune by a lot and get into a regime where we're mainly dominated by sort of unitary or Hamiltonian dynamics. So let me unpack in one more step, what's this J plus J minus operator sitting over here. And so if we unpack that, we can approximately rewrite this as total J squared minus the spin projection JZ squared. And so dynamically, this leads to two effects. This effect over here is what's called a one-axis twisting Hamiltonian. And so, for instance, if you imagine a classical sphere and I drew a dashed line on it here, essentially it's like a rubber ball, and this creates dynamics like I'm twisting this rubber ball in opposite directions on the north and south pole, and it causes a deformation. And if that were a quantum noise ellipse from, for instance, the fundamental spin projection noise of the atoms, then actually this would deform that noise and create entanglement between the atoms. The other term is this total J squared term. And that basically says, if I change the length of my block vector by, for instance, misorienting these spins relative to each other due to single particle dephasing, that would shorten the block vector, but there's an energy change or energy cost associated with this. So this is a term that might be helpful for actually providing gap protection in your system for maintaining single particle coherence. So I'm just going to briefly highlight that we've seen both of these effects. We can see the one-axis twisting that shows up dynamically as saying that the frequency that the atoms process in the lab frame in this fictitious block vector goes like 2 times chi times the spin projection JZ. And so we can actually look at the still there's a little bit of light leaking out of the cavity that we can use to track the precession of the block vector. And so we look at the frequency of that precession as a function of the spin inversion JZ, and sure enough, we see this change like you would expect up here. The other claim was that there should be this coupling constant chi out front, and that it should look like a dispersive. And so we can actually fix the inversion JZ somewhere down near the south pole. And we can look at the frequency of the light that comes out as a function of the detuning of the cavity from resonance. So previously, when we were talking about the cavity frequency pulling coefficient, and we were saying we were 500,000 times less sensitive to cavity frequency noise, it's because we were sitting in a regime right here. We were sitting very close to zero detuning, and that's how we're getting such a small coefficient in our system. But this gives you a more general picture of thinking of it in a spin language, where you can understand that actually in any regime, you can understand what the pulling is doing to you. This kind of one-axis twisting stuff, there's a proposal out of Vaughn's group, as well as from Amaria's group in our group, for how to exploit this to create entanglement. I'm going to quickly just say that we can also look for this single particle, a many body energy gap that goes like the total spin squared. This is a little bit complicated. Basically, what you're looking at here as a function of time is the black trace is just where the cavity is detuned from resonance, and we're seeing light leaking out of the cavity. Okay, this is superradiant emission. That's just residual. It's there in the background, but we're using that as our signal. And we can measure the phase of the light here, and we can measure the phase of the light coming out here, and we can actually take the difference between those two. But we can also do an experiment where we actually do the exact same experiment, but right here, right after we've made that phase measurement, we actually dephase the ensemble. We apply an inhomogeneous differential AC star shift between the ground and excited state that actually is very big. It essentially scrambles the relative orientation of all the spins. That turns off the superradiance in the system, and then we can reverse it. We can apply the exact opposite single particle dephasing and kind of re-lengthen our block vector, and we can ask what's the phase of the light afterwards. So what do we expect? Let's do a 2-spin half ensemble for this, okay? So this many body shift over here says that if I have 2 spins, I can have a J equals 1 and J equals 0 manifold, but because of this term, this manifold gets shifted up compared to the J equals 0 manifold. And it shifts up by 2 chi. So if I had prepared myself in a coherent spin state of the J equals 1 manifold, I might have amplitude distributions that look like so. Now, if I apply a single particle dephasing, essentially what I'm doing is I'm mapping, I can't change my spin projection JZ, but I can map the center part of this ladder onto a state of total J that's smaller. I can hold for some amount of time, and then when I reverse that dephasing, I'm essentially mapping back. And when I do that, the central part, this amplitude over here, gets a frequency shift, or I'm sorry, a phase shift that's proportional to this shift times the time I spend in that state. So this allows us to build a kind of now Ramsey interferometer, where this phase shift will show up in the phase of the emitted light after this dark period. So if we don't do the dephasing, here's the phase shift we observe as a function of T hold. But if we do the dephasing, actually we see that there's this additional phase shift, and this is a direct measurement of this energy gap in the system. Okay. I'm going to skip over this. We also, in that same paper, had looked for signs of the many-body gap leading to a kind of spin locking, or actually keeping 2 objects that would like to precess at different frequencies from precessing at those different frequencies, but instead kind of locking to each other. And so we have some signatures of it. We can change the sign of chi by changing the sign of the cavity detuning. And we can see features that actually change psi here. I won't go into the detail. It agrees with the theory. It's coming about from this kind of many body gap. But actually, there's a recent paper out from Monica's group where they saw this using Raman transitions, and I'll encourage you to go look there. It's a really beautiful experiment. I'm going to not pause for questions here. I'm going to go through one more section, and then we'll pause for questions, because this is very related. So I'm going to talk about another experiment we've been doing, thinking about this field of phenomena out of equilibrium. And so in normal many body physics, often you're thinking about find one state or the equilibrium of the system by minimizing some friction. Okay. But in atomic systems, we're really good at driving our systems out of equilibrium. And in fact, people have looked at non-equilibrium phase transitions in open quantum systems at ETH and Stanford and Hamburg and Tübingen and MIT and Berkeley. Lots of really beautiful work being done in these fields. Uh, we're going to work in a regime that sometimes is referred to as dynamical phase transitions in closed systems, where in fact, essentially, we're not going to have an open quantum system. The dynamics we're seeing are going to be governed more by Hamiltonian dynamics purely. And we're going to, for now, work with have a working definition of this dynamical phase transition as an abrupt change in the dynamical behavior of a system as characterized by a time averaged order parameter. Okay. Now, this word is used to mean different things by different communities. So there were experiments at RF ion traps in Innsbruck and cold atoms in Hamburg that actually referred to more of a Low-Schmidt echo kind of experiment. That's not what we mean here. We mean more along the lines of experiments that were done previously at JQI and Chris Minogue's group and at Toronto, thinking about more of sort of a collective oscillations of the system that you observe as a function of time. So if you want to sort of compare it to literature, we're using it more in the sense of these experiments. Okay, so the work that I'm describing is in this paper here. Again, this is a collaboration with Anna Maria's group here at JILA. And what we're realizing is sometimes called the Lipkin-Meshkov-Glick model. I sometimes get lost on names. I'm bad with names. So here's the Hamiltonian, right? It's this. We're making a Hamiltonian that looks like spin exchange plus a transverse field, which would drive Rabi flopping, plus a detuning of that transverse field, which looks like a longitudinal field, delta. Okay. And the order parameter here is going to be the time averaged magnetization, the spin projection along JZ, which is the population basis. So JZ is plus n over 2, all the atoms are in spin up. If it's minus n over 2, all the atoms are in spin down. So it turns out you can calculate a phase diagram for this. I'm not going to sort of focus on this too much. Instead, I'll just jump straight to the experiments. But suffice to say that we're going to show that there's a paramagnetic-like phase and a ferromagnetic phase in a 2D phase plane defined by the detuning, the longitudinal field, and the transverse field, omega over here. So I said we have this Hamiltonian. How do we program it? Well, let's actually focus for a moment on these two terms up here. The way we program this is by actually driving field using a laser that we inject into the cavity mode over here. The field strength sets omega for the transverse field, and the detuning from the atomic transition frequency sets delta, but we also have a phase degree of freedom, which is the phase of the field that we're injecting at any given moment in time. Here's the frequency picture of what's going on. Here's the cavity. It's very far detuned from resonance. Rather than working with the millihertz transition, now we're working with the 7.5 kilohertz transition that allowed us to speed up the dynamics and get away from some single particle decoherence that was hurting us. The probe is going to be detuned from the atomic transition by some small amount in delta. And that's typically going to be around 0, but it might go from -2 to +2 megahertz. And again, all of this is very, very large detuning compared to the detuning from the cavity. And that means that superradiant emission is going to be negligible for these experiments. So it really acts like largely a closed quantum system. Lastly, at this large detuning, to give you a sense of scale of the system, if I have n times chi sets the characteristic energy scale in the system, this is of order plus or minus half a megahertz. It can be minus by actually flipping the sign of the detuning of the cavity to the other side. So here's the expected phase diagram, and we're going to first look in the experiments in the limit where the detuning is equal to 0. So actually now we're just reduced to this Hamiltonian. And the idea is that we'll go through a ferromagnetic phase into a paramagnetic phase if we were to follow a trajectory along this line. So we're really exploring along this line over here. So it's easier to explain these phases by actually just saying, what do we see in the experiment? So we can actually, for instance, put ourselves here, and we see that here's the time dynamics. Here's the spin projection JZ normalized to the n over 2 total atom number. And what we see is when the transverse field is very weak, we're actually dominated by the spin exchange interactions. And that actually causes the atoms to be trapped near the South Pole. They can't get away from the South Pole. As we move further up, we see that now actually we're in a regime where the transverse field is bigger and we can start to move away from the South Pole. As we continue up the phase diagram, we see that we can actually get all the way to the equator, and then we find we settle at the equator until we're on the other side. So this phase transition is essentially this sort of going from being stuck near the South Pole to actually overshooting and beginning to Rabi flop. At this end, actually now the transverse field is completely dominate. The spin exchange is just a small perturbation, and you're just seeing single particle Rabi flopping. We're doing these experiments in a standing wave cavity. So in fact, there's inhomogeneity in the Rabi frequency or the transverse field associated with what we're applying. And this causes the atoms to get out of phase in the Rabi flopping, and that's what causes the damping here. So now in order to sort of more smoothly sample along this line, what we'll do is we'll look at the long times over here at around 4 microseconds in a small averaging window. We'll look at the spin projection JZ there. And we'll do that as a function of the transverse field magnitude. And so that's what, again, here's moving along this line. And what we expect to see is this kind of behavior, okay? And this is it. So at 0.3 million atoms all the way up to 0.9 million atoms, that's the different colors here. Here's the transverse field magnitude. And in fact, we see this sharp transition behavior in the system. We can actually rescale the transverse field by the interaction strength because it's really the ratio that matters. And we see that these curves all fall on top of each other, okay, and they collapse. And this black curve is a theory curve for what we expect in the system. Again, at this end is where we expect the spin exchange interactions to dominate. We stay near the South Pole. Here's where the transverse field dominates, and we actually can come up to the equator. And this is the sharp transition between a ferromagnetic phase to something where you say the spin projection JZ goes to 0 because they're all Rabi flopping in time. Okay. So we can also explore along a horizontal trajectory here, and where we actually hold omega, the transverse field fixed, and we actually scan delta. And we can do that, say, for this trajectory down here. And when we look, so this is the blue trajectory, we see that ignore red and blue. It has nothing to do with the red and blue here, okay? Let's actually just choose for a moment that we've chosen the cavity detuning so that chi is less than 0. Then as we actually scan the frequency from one trial to the next, we see that we don't get atoms moving towards the North Pole at a detuning of 0. We actually see that it's shifting. And actually the characteristic size of this shift is actually of order chi n. We can flip the sign of chi and we see that we shift in the exact opposite way. And what we're really seeing is that the atoms are staying trapped near the South Pole. And essentially this cross section is essentially the cross section you see here. Okay. We can now actually work up here and do the same experiment. And so at much larger omega, and now we see this, again, let's just focus on the blue. And so we see something that's beginning to approach, losing control of PowerPoint. There we go. For the blue, we're seeing something that's beginning to approach essentially the envelope that you would expect if you just had single particle Rabi flopping in your experiment, which is what the gray bands are. So clearly we're moving away from single particle physics. The interactions are really important for understanding the dynamics in the system. So together with the fact that we've explored trajectories along this way, we've really fully explored this phase diagram. And one other thing that's unique in these systems is that when you have these dynamical phase transitions, actually what you observe in terms of phases depends on initial conditions. So I won't go into detail, but I will say that we did experiments where before running the experiment, we could prepare the block vector describing the atoms at an arbitrary point in the southern hemisphere. And then we could actually look at the phase diagram when we actually scan, in this case, omega, when we change omega in the system and operating at delta equals 0, but we can essentially look at, when do we actually stay trapped near the South Pole, and when do we break free and make it up above the equator? And that's the blue region over here. And so we can compare experiment and theory, and that has good agreement as well. So in conclusion for this section, I'll just say that we were able to realize the slip-game mesh conflict model. In the future, we're interested in interplay between disorder and dissipation in the system. We are really interested in moving beyond 2-level systems. In strontium, we can have up to 20 available levels to us. And thinking about, could we ever get ourselves into a technical regime where we could actually look for the generation of entangled states? So I'm going to stop there for questions.
Okay, great. So we have a few for you. So our first question is from Bill Phillips. He says that in the hydrogen maser, there's cavity pulling, which for an oscillating maser is first order in the detuning and dependent on the atom number, and that it's often compensated by spin exchange. so that you can cancel both together. Is there anything similar here?
We haven't, I know what Bill's talking about. We haven't thought of that mechanism. So just to be clear here, what I'm calling spin exchange plays the role of the cavity pulling in the hydrogen maser. And then what Bill, I believe, is referring to is the fact that you can have sort of a density dependent shift due to collisions. And that is sort of a direct spin exchange because atoms are bumping into each other, not because you're exchanging microwave photons, okay? And they can balance those against each other to become, to play them off against each other. I don't know a way to do that at the moment in our system. So no, I haven't identified anything like that yet.
Okay, and John Simon has one for you. So his question is, what happens if we add Rydberg-Rydberg interactions between the atoms? Because it seems like it would suppress the flip-flop with a local Ising term, and is that useful?
You know, my sense is yes, that would be a lot of fun to do. Pretty much if you introduce any kind of new interaction into these systems, people get excited about it. So if you could combine short range interactions with, well, in my world, what I call short range interactions, I know Rydberg interactions are sometimes called long range. In my world, I call them short range interactions. If you combine that with the long range interactions of a cavity, I can imagine there's lots of models that you could try to emulate.
Okay, and then our next one is from Mehdi Hassan, and he asks, in the experiment on the Lipkin model, what's the estimated number of neighbors that an atom interacts with?
Essentially all, up to the fact that we have inhomogeneity in the coupling to the cavity. So these are all-to-all interactions.
Okay, thank you. I think that's about all the questions that we have for now, so we'll let you keep going.
Sure. So I'm going to give some quick summaries of the various parts here, because I know we're getting a little long on time. So I just want to give an update that we've done work in my lab looking at phase sensing below the standard quantum limit. And this is a fundamental inability to know the orientation of a classical block vector when you include the fact that it's not just a classical block vector, it's actually a quantum object, and there's some quantum fuzziness in its orientation. And the goal here was to create large entanglement enhancements for quantum sensors to show that that's doable. And the basic idea is that essentially you can use a measurement process where you say, if there's some quantum fuzziness in the orientation of my block sphere, I should just go measure its spin projection JZ, and now I know it, I've localized it. And so for instance, here's some data where you just say, well, look, I start with some coherent spin state, it has some quantum fuzziness, and that leads to a trial-to-trial variation in the measurement outcome of the spin projection JZ, labeled J sub Z final. And we can do that for two different polar angles of states that we're preparing. You can see that it's hard to push them from each other on a single shot. So we can do a related experiment where now, instead of just doing a single spin projection measurement, we can actually also do a pre-measurement and look at the difference between the two. What we see is we can actually partially cancel off the quantum noise via what's called this quantum non-demolition measurement. So by making a pre-measurement of the quantum noise, applying a phase shift, for instance, it could come from a Ramsey interferometer, we can subtract the quantum noise from the final measurement while still maintaining our phase signal. And so we create these, sometimes what you'll picture as these kind of spin squeeze states is what they're called. This idea was proposed in '98, and there are other groups doing this, including we heard about 2 or 3 weeks ago from Jakob Reichel's group with a recent result. So I just want to remind you how this works. In this case, we're doing it in rubidium, and so our spin half state. Here we essentially we shift resonance frequency depends on the essentially the matrix where let me make sure I can shift networks. Is it any better?
I think you're still pretty slow.
Is it any better?
Yeah, that looks like it's good.
Okay. Okay. Let's write it. We'll see how far we get. The idea is that if I put atoms in spin up, I get a shift that's proportional to the number of atoms in spin up, and also the coupling strength to the cavity, as well as the overall detuning from this atomic transition, 1 over delta. So the idea is if I know g squared and delta, then I can actually extract from this frequency shift the number of atoms in spin up. Really, this is just like saying atoms in spin up, they act like pieces of glass with some index of refraction that I've inserted inside the cavity, and that causes the effective path length between the mirrors to change, and that shifts the optical resonance frequency. But by making this measurement, we figure out how many atoms are in spin up, but not which atoms are in spin up. This is an important concept that we'll come back to in a little bit. So I'm not going to sort of go into details of how we do this and whatnot. I'm just going to mainly give you a summary of my best understanding of where the field stands. What we've plotted on the horizontal is year, and then on the vertical is the improvement over the standard quantum limit expressed in variance. So keep in mind, this is a log scale on the vertical. 1 means that you're at the original unentangled quantum noise level, and a bigger number is better. It means you're going to sense phases better. And so people started doing experiments in ion traps, and for instance, in Dave Wineland's group, just down the road here, and in Rainer Blatt's group. But people also started figuring out how to let atoms collide with each other to generate entanglement, sort of one-axis twisting style dynamics, as well as using cavities to generate entanglement in non-classical states. And so those are the solid dots, or these cavity experiments. And so our group's work is in red here as a function of time. And so in terms of the directly observed amount of squeezing, at the moment it's sitting, Mark Kasevich's group at Stanford and our group are up around 18 dB is the rough number. And they're about a dB better than us, okay? And so this is actually a lot. It's about a factor of 60 beyond the standard quantum limit is what we can do. I want to emphasize this is directly observed. There's no like, oh, well, I subtract off, I had a bad amplifier somewhere in my system, but I know it so I can characterize it and so on for it. This is the actual observed squeezing out of these systems. So I just want to tell you that where we're going with it in the group, looking forward, and this is being led by Graham and Bao Chen and Chengyi, is actually working to map this entanglement onto matter wave interferometers. And so we figured out a way to actually guide the atoms along the cavity axis so we can actually let them fall along the cavity axis. And this is a function of time, seeing the cloud from the side. We've shown that you can actually get 11 dB of spin squeezing using time average measurements where you add time average over the inhomogeneous coupling to the cavity mode. And so we can create these spin squeeze states that now is in a spin basis. And what we'd really like to do is now entangle the spin degree freedom with emotional degree freedom, a momentum state in the system. And so that would allow us to build a matter wave interferometer for sensing other types of things, not just clots, but for instance, inertial sensors. So in fact, I'll just give you the update and then not go any further into it, just to say that we're at a place now where actually we're running an interferometer inside the cavity and we can actually see fringes that don't quite have the contrast we want, but they're getting there. It's sort of in the 70% kind of range. And so what we'd really like to do is marry this squeezing to this interferometer and do a proof of principle that we can really get some benefit in the system from using non-classical states. So I'm just going to briefly give a quick overview that we've also been doing this experiment back in strontium. And a paper just appeared on the archive yesterday describing this, which I like to think of as, avoiding having to do an atomic pitch drop experiment. So if you don't know the atomic pitch drop experiment, you've got to go to Wikipedia and look this up. Like, it's a fun thing, right? Back in 1927, some guy poured some hot pitch into a funnel here. And it's really thick stuff. It doesn't like to flow. And in fact, it took 11 years for the first drop to fall out of the bottom of this funnel. And that seemed like a fun thing. So they kept the experiment going, and now it's 2014, and the 9th drop has actually fallen out of this thing. It's a really, really slow experiment, and you have to have a lot of patience to pull this off, right? Well, it turns out that when you get these optically excited states like we're using that live a very, very long time, actually it can be challenging. You can do it, but it can be challenging to wait around long enough for this excited state to decay to the ground state. Because it's living for, at the moment, our best estimate is that the lifetime is 145 seconds plus or minus 40 seconds. And it turns out that this best estimate of the lifetime of the clock transition, it's not from doing a pitch drop experiment. It's not for waiting for the atoms to fall. It's from actually measuring the differential G factor between the triplet P0 state and singlet S0 state, combining that with atomic structure calculations, and be able to infer how much of another state is being mixed into triplet P0, which then tells you how fast it decays, okay? And this was done here in Juni's group, okay? Okay, so we are also impatient folks. And so we're going to try and figure out a way that we can try and measure the natural lifetime of this upper clock state in strontium by using measurement pulses that last 10 milliseconds, not hundreds of seconds. Here's the basic idea. It's really using the tools that were developed for creating non-demolition measurements. The idea is that there are two atomic transitions out of the ground state in strontium. One is this millihertz transition, the other one is the 7.5 kilohertz transition. So the idea is we will send two probes into the cavity for the same ensemble of atoms in the ground state, and we will measure the phase shift imposed on a probe near this transition, while also measuring the phase shift on a probe near the 7.5 kilohertz transition. And then there are other things you need to know, but roughly you can say that we can determine the natural line width of this very narrow transition in terms of the line width of this transition, which is really well known, to the ratio of these phase shifts. That's the trick. We're essentially measuring the differential strength of the coupling of these two atomic transitions to the cavity mode, because that depends on the matrix element squared. So we can, this transition is more normal standard. I'm looking for a cavity frequency shift. This one operates in a more funny regime, so I'm just going to show you 2 slides of data on that. So we can actually tune the cavity onto resonance, and here's, and look at the transmitted power. And so this is in hertz here. So it's, plus or minus 200 hertz. The cavity line width is 145 kilohertz. So in fact, you're not even seeing the cavity line width. It extends way, way, way off the slides. Okay. But what we see is right in the middle, we see 2 dips in transmission. And the reason it's 2 is because we have half the atoms in minus 9 halves and half the atoms in plus 9 halves when we do these experiments. So we're seeing the direct absorption enhanced by the high finesse of the cavity of this probe by this really, really weak transition. So if you can see absorption, you can also see phase shifts. And so to see the phase shifts for a reason to get rid of technical noise, phase shifts in the system that can hamper your precision, we can do the experiment where we send in 2 probe tones now close to this transition, this very narrow transition, and we can look at the difference phase between them. And so as we scan the frequency of the center of these 2 probes, if the atoms are in the ground state, then we see a dispersive shift when one probe tone passes through resonance, and then as the other probe tone passes through resonance. Actually, this is such a long-lived state, we can actually do something you normally don't get to do. We can invert the system. So we can put all the atoms in the optically excited state, and we can do the same experiment. And sure enough, you see the sign of the phase shift flip side, because this is such a stable state up here. So from the size of that phase shift, we can actually determine the natural lifetime of this transition. Previously, the best number was 145 plus or minus 40 seconds. Now we can determine this to be 118 plus or minus 3 seconds, or an equivalent line width of 1.35 plus or minus 0.03 millihertz. So that means we have 30 microhertz resolution on this lifetime. That means that we could, in principle, observe a state that lives for 1.5 hours. We have enough precision in the system. In fact, most of that error bar is dominated by some fractional errors, so probably even better. With a few improvements and changing, you could imagine measuring states with lifetimes of 15 hours, day kind of scale. And again, this doesn't require you trapping those atoms for that amount of time at all. This is all being done with very, very short probe pulses. So I've told you some experiments about how we're exploiting many atoms to create correlations and entanglement between the atoms. And I really want to emphasize that this seems like a really powerful tool. It's really well impedance matched to many experiments you want to do in metrology, in terms of, well, it's pretty straightforward to think about putting an optical last clock in between those mirrors, for instance. But it also has a range where it allows to maybe look at interesting models of quantum many-body physics. and even open up the possibility, like John was mentioning, for instance, combining infinite range interactions with short range interactions in these systems. I didn't do this work. Students and postdocs did this work. They did a wonderful job. Julia Klein and Juan Munez, Dylan Young, Matt Norgia, and Matthew Winchester on the strontium experiments. And then Graham Greb, Bao-Chen Wu, Jingyi Liu, Denton Wu, and Kevin Cox, and then former members on the rubidium experiments. And we really benefit here at JILA from having a very, very collaborative environment. And so very appreciative of all that, plus funding. And my last thing will be a plug that if you're interested in looking for postdocs, you can apply for NRC postdocs to work with our lab, and they pay really, really nicely. So if you're looking, we'd love to, it'd be great to talk. So thank you.
Okay, great. Thank you. So we've built up a few more questions for you here at the end. So we have another one from Bill Phillips. He says that you said that the atoms were confined longitudinally in a 1D lattice, which is transversely in the Lambdicki limit. Is the confinement strong enough that there are no direct collisions?
Yeah, so the at the moment we don't see, let me be careful. We don't see any evidence that direct collisions are causing a, as a source of decoherence. That's where I want to be. We don't see that, but what we do see is the beginning of hints that there is a density dependent shift due to collisions that we might have to take care of when we think about accuracy for a superradiant laser. So we do see a small shift in that. At the moment, the atoms are confined over, our cavity length is, around 5 centimeters, okay? But the atoms are actually only using the central about 1 millimeter of that cavity. So you could imagine you could get some wins, maybe a factor of 10, by actually allowing the atoms to spread out along the cavity axis and while maintaining the total atom number the same. You can start to pull that number down.
Okay, so that actually leads very nicely into the next question that we have, which is from Monica. So she says that the Lipkin-Meshkov-Glick model is permutation symmetric, but your analysis focuses on times where inhomogeneous coupling has led to dephasing. So how would your results in the dynamical phase transition be different in a uniformly coupled system as opposed to being somewhat spread in the cavity, making it even longer, as you were mentioning?
So I don't think spreading out in the cavity is the key thing. It's really the inhomogeneity. So for instance, if we could get more homogeneous coupling, we have some ways that we're actually playing with in rubidium to finesse our way to more uniform coupling that might be applicable to strontium. But I want to go, sorry, let me start going click and get to a picture. Apologize. That's the one I want. Okay. So this is essentially a signal particle regime where what you're seeing, in fact, you can predict this. It's a Bessel function response to lowest order when you have inhomogeneous coupling. So you can get an analytic expression for it. One way to think about what's happening is that as the atoms begin to Rabi flop with respect to each other, some go a little bit faster, some a little shorter, and you're a little slower, and you shorten your Bloch vector. And when we think about the interaction strength, I've been using chi-n as the effective interaction strength, but what you should understand is dynamically as a function of time, the effective n, what's really here should be the Bloch vector length, is shrinking. And you're also getting a little bit of movement about where you are in the phase diagram as this thing shortens. So this shows up here. So for instance, imagine that I'm below the phase transition for this curve, but you see I'm beginning to drift upwards. That drift upwards is because, in fact, what's happening is the Bloch vector is beginning to shorten due to all this sort of mutation, the rotation in the system. And so what happens is you're actually beginning to kind of self-tune towards the phase transition. And if you wait long enough, eventually all the atoms will start Rabi flopping again.
So we have one more from John Simon. He says that looking at your group squeezing versus time on the graph, you seem to be on a line of about 3 dB per year. So should we expect 27 dB this year?
Yeah, that's a good question. Is it though? Okay. Are you nervous? I'm about to say yes. No, we haven't been pushing. We haven't been pushing in that direction. It's really been pushing on the, let's try and apply it to a different type of system. What I will say is that in rubidium, it turns out that what we're using to make this rapid progress in our system is we're actually doing our QND probing on an optical cycling transition. And it turns out that it changes the fundamental scaling in the system to a more favorable scaling with n times a single particle cooperativity parameter. If in rubidium, because of the finite ground state hyperfine splitting, it turns out it's not really a true cycling transition. That laser beam can interact with atoms in the f=1 state, for which that same light can scatter and flip the spin state via spontaneous Raman transitions. That changes the scaling. And so what happens is that once you get above about, like 25 dB, the scaling flips over to a much harder scaling. So I'm trying to get at the idea that actually in rubidium, it's going to be really hard to push past, like 30 dB, okay? You'll run into all kinds of technical issues before them, but that's going to be sort of a more fundamental scaling. The good news is that in systems like strontium and ytterbium, Vlon's recent beautiful work with squeezing in ytterbium and a clock measurement in ytterbium, that in those systems, actually, they're really, really great cycling transitions, where you could imagine that as you continue to figure out how to beat down technical issues, yeah, like the amount of squeezing you could get in those systems one day could be huge. The challenge will always be rotating them in a way that your local oscillator doesn't erase your ability to confirm the existence of the entanglement that you're generating. Actually, the local oscillators are the hard thing.
So I think maybe since we're planning to have our discussion session afterwards, we can sort of postpone any outstanding questions to then. And I want to hand it over to John. So if James you can stop sharing your screen, then
sure thing.
John will give us the information about upcoming things.
Okay. I want to, there's the button. There it is. Okay, great. So thank you all for coming today. It's always a pleasure to have this and to have all of you join us. We wanted to remind you of 2 upcoming virtual seminars, one from our sibling series, the Quantum Science Seminar, which will be Antoine Brohuis from the Institut d'Optique. And that'll be next Thursday at 5 o'clock CET. And then Vamos will be back with you next Friday at noon Pacific time, and our speaker will be Norm Yao. So please join us and join the Quantum Science Seminar next week. And in the interim, enjoy your weekend.